Great. This is the first place winners call for the Universal Image Embedding competition. Andre, I'll have you introduce the host teams.
Sounds good. Hi, everyone. I'm Andre. I think we already met at the very least in the workshop virtually, Xiao. So yeah, I work in Google Research, leading this competition and work on computer vision. So maybe next from our side, Bingi, who I think you're already familiar with too, but maybe you can say a few words, Bingi.
Sure. So I'm Bingi. So the same as Andre, I'm also working on local image features. So I think I know Shihao pretty well because we continued some research, which carries some of the results from the Universal Embedding Challenge. Yeah.
Cool.
So Kaifeng, please go next.
Yeah. Hi, Shihao. This is Kaifeng. I'm also from Google Research. First, congrats on winning the first solution. Yeah, it's really amazing to me. For me, I'm working on the internal features for different Google use cases, and I think your approach actually sort of is really inspiring for even for internal model training. So I would like to hear more about your approach, and yeah, that's it.
So I'm Shihao Shao from the Peking University Health Science Center, and as I mentioned before, I'm in my fresh year of my PhD. So it's really my honor to have to get the first place in such a big competitions, and I know it's a new series after the landmark series. So I'm really happy to be here, and thanks for having me. Thank you.
Great. So you can start presenting your slides now.
Okay. So I just share my screen, right?
Yes.
Okay, let's see this. Just give me a second. And can you see my screen?
Yes.
Okay. So let's get started. But honestly, I have just do the presentation in the ECCV conference, so there's many of stuff that has already duplicated. I mean, comparing with the presentation in the ECCV, so something I may just skip or I just speak quickly and I just focus on something that I have not mentioned before. So here's the background of me and my professor.
We can only see the first screen.
Okay. Okay. Let's
there we go.
try. Maybe I just need to share the full screen. Let me see. Okay. Let me see. So can you see I'm changing the slides?
So you're no longer presenting?
Oh, okay. So can you see my screen now?
Yes.
So I'm changing the slides?
Yep, absolutely. Now we can see it.
Okay. So I will just give the presentation more quickly than the ECCV version. And let's just jump into the methods part. And so in a nutshell, we use the multi-stages train and we just apply some tricks during the training. And here's the tools we use, like some frameworks like PyTorch, and the all training pipeline is just write by me and my professor. So we did not use any sort of packages from GitHub or something like that. And for the training time cost, it's just really 10+ days. And for the dataset selection, which I think is a really important part, or I'll say the most important part in these competitions. So here I wrote a pseudo code for how to select the datasets. Well, honestly, I don't have to do that, but because it's really easy, I just add the data sets. I just collect the data sets as much as possible. Although I spend much time on that, but I still think that it is the most important part in this competition, since we don't have a training data sets and also the validation and test data sets. So we need to collect the data sets by our own, and these steps is really important. So it's kind of easy that we just collect the data sets and put them into the training list and train the data sets with this new data sets, and we just see if the accuracy, or i.e. the matrix, is raising or not, and that will determine that whether we need to keep this data sets or not. So this routine just works like this pseudocode you can see from that. And here I list the final chosen data set in this competition. So the most important one is product 10K, which is really important and powerful. So I can tell from this paradigm, when we try to find the data set and just try to use them, we find that the product 10K is really important. So that's why in the following pages, I will mention that we leave the product 10K individually for the fine-tuning part and use the rest of the whole data set for the pre-training or for the training. And here is some commentating about the training. So we use SGD. Well, there is some issue about the choosing of the optimizer because, some just paper have mentioned, and through some experiments also I'm aware of that if you want to get a high generalization capacity, then the SGD is much more better choice than the ADAM, So we choose SGD with a momentum of 0.9, and for the mini batch size, we choose 1024 and 256 for FC layer and the backbone respectively. But I would say I don't consider for the time cost, I will choose relatively much more small size of mini batch size, because if you want to get a high generalization capacity, you need to use some small mini batch size. But in this competition, the data sets we need to train is really big, so we just try some big mini batch size because it will accelerate your training process. So if I don't consider the time cost, I will choose maybe like 128 for the FC layer and like 32 for the backbone, because the backbone is much more easier to get overfitting. It has much more numbers of ways, right? And for the learning rate scheduler, we just use the initial learning rate of 0.02, and we train that for the FC layer. We train that for 6 epochs, and we use a decay for 0.1, and something like that. You can just see from these slides. So our training is divided into 15 stages. But there are many things that is duplicated, so it's just repeat one by one. And I will just introduce some of them. So in the first early stages, like the stage 1, the first stage, we just, as I have said in the dataset selection part, that I firstly use all the datasets only except the product 10K. Oh, sorry, I hear some noises from my cat. So I will use different all the datasets except the product 10K, and we only train the last 2 layers. It's because the backbone is already well trained, but the FC is just from the scratch, so it's not get well trained. And if you just put everything to train together, you will just got the backbone weights got vanished, right? So we just firstly train the last 2 layers. And here let me just use a different pointer. Let's see which pointer should we use. So this one, okay. So this FC layer, the first FC layer to just embedding the feature to 1024, this FC layer is come from the pre-train weights, aka the weight H14 trained on lane 2B. I have seen some threads that they just throw out these FC layers and they only use FC layers to control it to 64, but we did not do that. We use an additional FC layer to just make the embedding spaces to 64 dimensions. But some threads reported that if you just get rid of this FC layer, the performance will raising. I'm not quite sure, but maybe it's a better choice. Anyway, I just leave it as it is. So I train the last two layers with some settings like the arc phase, the M of 0.5, and I train for 6 apples to make it converge. And then after it's well trained, I just freezing the last two layers and unfreeze the rest of the part and retrain that. And in this whole process, the image size is 224. I mean the resolutions. So then we can just fine tuning on the product 10K. So the training process is basically really similar to the first two stages. So first we train the last layer, but here we use additional stages to train the middle FC layers. And then the stage 5, we only train the backbone. And also the dropout here is just additional added because, you know, in this competition it's easier to get overfitting. So I just add an additional dropout. And in stage 6 to 10, I just repeat the 1 to 5 with a large image size 280, and I just increase my arc phase M. So here's an issue that I find that if I just, you know, to raise up the M in the late stage of the training, it will help the whole training process. I think it's reasonable because if you just set a very big M, very high M, like 0.9 or something like that, you will the model will just get hard to get converged to a certain stages, you know, like you have a very strong power to just pull the vectors of each classes to the same one, and you just make the different vectors from the different classes aside, but the power is too strong to let the model converge. So I think you need to use a relatively small M in the early stage and just raise the M in the late stage. And also, it's not only from my intuition, I just do some experiments, i.e. ablation studies. So I also find this phenomenon that if I use, so like in the stage 6 to 10, if I use M of 0.55, it's much more better than we just keep the same M equals 0.5. But I don't remember how big is that gap. So in the previous data set, I mean the test data sets in Kaggle platform, it should be like 0.0005, 0.006, something like that. And after the 5 stages, I just increase the image size again for another 5 stages, but with 4 pixel overlapping in patches. So this approach is I have an ablation studies here. So the one solution is just like I write in this slides in stages 11 to 15, I use duplicate overlapping patches. So another solution is that I can use the same computation resources to get a much more bigger image size, but no overlapping in patches. So I have some calculation to control all the, you know, the computation load is the same, but I don't remember how big is that image size. Anyway, it should be beyond 300, but that one is worse than this one. I'm not saying that overlapping in patches is better than the image size increasing, but I will say there's such a trade-off between these two stuffs. Since I have already just raised up my image size, so it's time to just give some overlapping in patches. So it's from my intuition to give the reason, but I don't know if that is right. And here I list some findings. And also these findings has already been mentioned in the ECCV conference. But let's just mention it again. So this basically from the experiments about width L. So width L is a really good base because width L is not that big. I mean, comparing with the width H. So we have the room to do the ensemble. But if we do the ensemble, some interesting may just show up. So, you know, like in the width L stages, I feel like this competition is getting much more interesting because it involves with much more like trick and something like that. But, you know, like in the late stage, we have width H, so we don't have that much of room. But anyway, so in width L stage, I find that the ensemble is not that easy in this competition. I mean, if you just do the ensemble in this competition, all you need to do is to just take the average of different embedding from different models, right? Because we need to control the final embedding spaces the same length. So if we do that, we'll find that the ensemble in this competition is not that working. It's not working, but it's just even much more worse than we just use some single model. So it's very like counterintuitive. And I just want to dive into the reason. And I want to mention before I just say that is that these things all from my intuition and it lacks of some, you know, experiments to just prove that. But oh, okay, I just see my idea about that. So why the perform is bad in the competition when we use ensemble? So basically, I think it's because the embedding spaces is not the same. It's not elegant between the different embedding spaces. So you can just see from this screen. So in this slides, so let's recall what things is really important in just creating a subspace for the embedding. So it's the things that's really important is that the distance between each classes, you know. So I will say these two spaces is all the same, although they just look not the same, right? But if you just see the distance, they are all the same. So like red and yellow, we have 180 degree, and red and blue is 90 degree, right? And here, red and blue, red and yellow, 90 and 180. So I can see these two subspaces is equally to each other. But if you just try to do the traditional, they take the average of different embedding spaces, you will get a distorted space like this one. Red is really obvious because, you know, the blue is here and here the blue. With this blue has 180 degrees. So when we just summarize them up, we will don't have the blue and the green, right? So in real life, I mean, in the real routine, the spaces may look not the same, but I just want to use this example to say that the spaces will get distorted because of the inconsistency between the different subspaces, okay? So here I just find some ways to get rid of this issue. So first, we need to know what we need to do to get rid of these phenomena. So what are the line here? I mean, the red line, the blue line, the yellow line, the green line. So they are all the central of different classes, right? And also in model form is the weights or the parameters of the last layer. So i.e. the height. So if we have a height, let's see, can we get a pin? Is that a pin? So if the last layer has, oh, let's see. So if the parameters of the last layer has a shape like that, so which means here's the classes and here's the embedding length. It just denotes the central embedding vector, the direction, because we use our face, right? We do normalization. So it's the central direction of each class. So all we need to do is just control the last layer, the FC layer of different models the same. So once we can do that, we can do the ensemble. And here I do some experiments. So there are several ways to achieve that. So the first one, sorry. I'm not totally got rid of the COVID, so there are some symptoms. So the first method is we can just train a let's say we train a model. It's f subscribe w and g subscribe w of x. Okay, so we train that like for 6 epochs. Oh, okay. Oops. 6 epochs, and we want to fine-tuning this model. So there's a paper called Model Soup. So they do the not exactly, but somewhat same as what we did here. Is that we can just try different hyperparameters to fine-tune this model, but with the last layer freeze. So with the last layer freeze, you will get literally the same last layer across different models, right? And when you just finish your fine-tuning, you will get different hyperparameter for the G. So it's here I write down like, oh, dot prime subscribe 1, subscribe 2, subscribe 3 to denote different parameters of the G when we finish the fine-tune using different hyperparameters. And then we can use this series of models, this stack of models to do the ensemble. And we find the performance is much more like what the ensemble should be like. So I don't remember the exact number, but it's like if we do the single model inference, so there's a model like 0.6 and 0.66 and another is 0.662. And if we do the naive ensemble, you know, the version of the space distorted I will get is something like 6.64. And if we do these approaches, we will get not exact number, but it's almost the gap in what we have experiments. Okay. So here we have another different way, and this way I have already do the experiments. It's not that good. I mean, compare with these methods, but I'm not sure if there's better solution to do that. I mean, using this idea, but for now, it's not that work. Okay, so we have an assumption here for this method is that the FW, I mean, how to say that? Let's see from the timeline maybe. So in these methods, we need to train the model from the very beginning for different settings. Now, for this approach is that we train the F subscribe W, G subscribe W, G subscribe W for certain apples and do the different fine tuning in this. In this approach, we just train the models with different settings from the very beginning. So we may get FW1, FW2. I don't write again for the G, okay? FW3. And we get this sort of FW, right? The space are now the same across different models. Then we need to choose a guide or a control parameters across different F. So we may choose in practice we may choose the which one is the most have the best score. I mean, for the matrix, we may pick this F subscribe W for the control group. But here I will just give an example. We choose W1, okay? So then for the rest of the model, so here it should be G subscribe W2 of X. So it picks this part. And through that here, through here, you can see from here, right? I use a linear layer T to transfer the embedding to the same spaces. And then we use a F subscribe W to control them. And we do the training again. So in this approach, I find that the performance is not that good as same as the rest of the method. Not the rest of, but the last one. It's not as good as that. It should be if we use a 0.66 and 0.662, it will get a 0.665 like that. Not that powerful. But I think maybe we need to add some non-linear things to the series of T here. I just use linear layer here, but maybe if I want to just convert the subspaces to the same one using the transfer layer, maybe I need to use some the activation function like ReLU or something like that to better change the subspaces. And that's all for my presentation. And we have a question and answer part.
Thank you. It's a very nice presentation with a lot of interesting findings and ideas. So I do have a quick question. So that's more related to the idea you talked about the model soups. So I think it's a little bit different from ensembling, because for ensembling, you usually just have to inference multi-models and get an embedding and then get the average of the embedding. But for the model soups, it's just like try to use different hyperparameter set to train the model, and then you kind of like average the weight of each model. So in the end, you actually only need to inference a single model, which is like the average of different models, like model soups. So that can probably give you a more bigger headroom, because you can have a much larger backbone. You can use the weight huge, and then to still do the kind of like model soup idea instead of ensembling, right? Or you are just trying to inspire by the idea of model soup to freeze the last layer and then try to see how the ensembling works for different features here.
Yeah, I just freeze the last layer. And model soup, this paper is really, I think it's really popular because it's beats the SOTA in the ImageNet 1K And what I do here is not exactly the same that the model should do. So the difference may come from that I did not do just the average of different models. We just do the ensemble. But I think you are right. If I just do the average of different model, the weights we may get, we may just be able to do the ensemble even on the weight edge. But like I have said, that the time cost is really high already. So the training time is already 10 days. So weight edge, when the weight edge is releasing, it's just have just like 15 days left before the competitions, and so we don't have that much of time to do the model soup again to average the weights. Yeah, but I will say maybe that is a good approach. I mean, to just comparing with just inference on the single weight edge model. Yeah.
Great, thanks. So another follow-up question. So I know like Clip, they released their pre-trained model like only 2 weeks before the deadline. So let's say if you are actually having more time or like you're not limited to the computation resource you have, so will there be some other like ideas you're going to further explore you feel like are very promising?
Well, in practical, I mean, practically, I will just use some if I just in this competition, I'm currently working on this competition, I may come up with different ideas. But for me, for that time, for now, I will say I will just stick onto the ensemble things. If I have much more time, but I'm not sure if I just have that much of time, I may just come up with other ideas. But I can't say that now because I have no idea now. Yeah.
Thank you. Yeah.
Yeah, I have a bunch of questions. The first question I have is about data set selection. So it looks like from your the slides, right? It's purely like a greedy selection. So you just add one data set and see and do the submission and see if it improves. If it improves, you keep it, and then you add another one. So is that the way that you select data set, or did I miss anything?
Yeah, that's the way I selected that. I did not do much of cross validation. I mean, in the very early stage of this competition, I surely do some cross validations, but I don't see that much of correlation in the late stage. So I need really cost of my time. So I just use the Kaggle server to do my cross validation.
I see. So basically, the data set selection is done by submission, sort of.
Yeah. Yeah.
Okay. And another question is about the training. I think in the end you have totally 15 stages, although some of them are just repeating each other by using different data sets, have parameters. The first is that the first is in the first few stages, I think you freeze the backbone, only train the projection, and then you did opposite. You freeze the projection and then train the backbone. One thing I want to make sure is that so from the backbone, then you have 1024 projection, and then you project that to 64. Yeah. And the first projection, the first FC layer, is actually trained in the CLIP model, right? The CLIP model already have that projection. So essentially, you unfreeze that one plus a randomly initialized 64-dimensional projection. Yeah. Okay, got it. And by doing this kind of training, do you see monotonically improved performance after each stage? Let's say from stage 1 to stage 2, do you see the improvement, or in the middle you see a performance drop and then somehow it goes back?
Well, basically just submit once like 5 stages. 5 stages is a repeating of the whole stages. So I just stage in the stage 5, stage 10, and stage 15. In such 3 stages, I find the metrics is rising. Yeah.
Okay. So essentially, so finally you find stage 5 is better than stage 0. Let's say stage 0, and stage 10 is better than stage 5,
Yeah.
and then 15 is better than 10. Okay, got it.
Yeah.
Got it. And then for the model assembling idea, so the assembling is yeah, I guess it looks more like a model soup to me, because in the end you are still try to average the weights and then make it only one backbone. I assume that is not in the final submission. You didn't have that in the final submission.
For example, I mean, when I use with.l, I do some submission because I have
see.
that of type. Yeah, with.l is not that big, but for with.h, I did not try them.
Because of the time and resources as well.
Yeah.
Got it. Yeah, thanks. I think that's all the questions. I have some other in mind, but I need to sort of forgot that. But Andrew, you can go first, and I can ask again.
Yeah, sounds good. Yep. First of all, congratulations again. So I just wanted to clarify a few things. So you're just talking about with.h and with.l. So the final weighting submissions with with.h, I think, right? So there's no ensembling there actually. But if you had time, you could ensemble. If there was computational resource, you could ensemble with.h and get better, like you observed in with.l. Okay, cool. So the second question I had was on the ensembling. I thought it was actually a quite interesting idea to freeze the classifier to force all the embeddings to kind of gravitate toward those classifier weights, and there's going to be some variance in where they will fall and you average in that constraint setting, right? So I just wanted to confirm my understanding. So when you're doing this ensembling, which is not the final model, but it's an interesting idea anyway, you actually average, right, the embeddings that are trained with the frozen. Is that correct?
Yeah.
Okay, cool. So I just wanted to make sure. And if I understood correctly, so you presented kind of two slides. There's one where you have the frozen classifier layer and you train all the embeddings, and you also tried adding a linear layer, but I think the first solution is the one that you found to work better. Is that correct?
I think so.
Yeah. So okay, cool. So yeah, I think that sounds like quite interesting idea actually. I don't know, not too familiar with the work on ensemble image embeddings. I think it's always something that people have a hard time doing, exactly for the reasons you mentioned. Like if you just train different embeddings, average them, the embedding space is going to be kind of mess. So it
I see.
looks like really interesting.
So in the first sampling approach, there's no weight average, right? It's just embedding average. So I guess I got it. Okay, so it's not model soup. It's really a sampling, but it just
got it.
Got it.
Only thing that is similar to model soup is that we use different hyperparameters to fine tune the model.
That makes sense.
So you start all the different model trainings from the same click backbone with different hyperparameters.
Yeah.
And all constrained with the same classifier layer, basically.
Yeah, exactly.
So if we can actually leverage the idea of model soups, so that maybe we can be able to still use the bit huge, still can be kept under the constraints of the Kaggle kernel computation time, and we may be able to make some further improvement on top of that.
Yeah, that would be great.
So regards like freezing the classification head for like different models to do ensembling. So will that approach, I understand that can make sure all the embeddings from different models can be constrained to the same dimension space, but will that actually limit the performance because like the classification layer is phrased, it's just like not trainable? Will that kind of like limit the headroom?
Well, intuitively, I think it's just for one layer, so you just freeze one layer, so it's not causing that much of performance decreasing, like you said, I think.
Cool.
I mean, I understand Binky's question because, like, it may be that So actually, how do you freeze this classifier? So I guess you trained an initial model.
Yeah.
And then took the classifier, froze, and then you train others, but with that frozen, right?
Yeah.
So it could be that this initial classifier was actually not optimal. So it
Yeah.
was not having some good class separations in some regions of the space, for example. So I understand Bingy's question, like potentially you could even like, well, it'd not be co-training, but if you could train everything at the same time and have shared weights for the classifier, then you're imposing that constraint, but trying to learn a better classifier given everything. But it may be very costly or something. I mean, you have to keep several different backbones in memory, so it may be infeasible.
Thanks, Andre. Yeah, exactly. I was trying to raise a question. You were saying here. I'm just so afraid like the performance upper bound will be limited by the initial model you train.
Yeah, maybe there is some room for improvement.
Mm-hmm.
Yeah, another thing maybe you can, I don't know, because we know that VH, if you train a VH, definitely works better than VL, right? You can take the classification layer trained by VH and use that to initialize a VL, and then do the same assembly. So,
Yeah, it's somewhat like a, how to say that, distillation. Yeah.
something like distillation. Yeah.
Very interesting, actually. Yeah, coming up with new ideas to try.
Yeah, I have just tried a somewhat weird thing is that I want to try some distillation in the ImageNet 1K, and I try something very interesting is to just when I train the ResNet 50, okay, and then I want to make it as a teacher model to train the ResNet 18, and I did not do anything else. I just picked the ResNet 50 as the last layer of the ResNet 50, and use this last layer, i.e. the FC layer, to train the ResNet 18, and it also got improvement in the performance. So the last layer, i.e. the central embedding of different classes, can be a teacher to just guide the training process.
Sorry, do you mean that you did exactly what Kaifeng said, but for ResNet models, or was there a difference?
It's just like you train the VH and pick the VH, the last layer of VH to train the VH, just like the Kaifeng has said. Yeah.
Yeah. Okay. So yes.
It works.
Yeah, it works in ImageNet 1K, but not that obvious. Like in the early stage, it's very obvious that there is a big gap between if we do such a type of the distillation, then we did not do that. But in the late stage, I will say the gap is almost like 0.3, 0.4, something like that.
I still have one question regarding the stages. So I guess so. You said that each 5 stages you group them together as one like big stage. Yeah, when you develop these training strategies, right? I assume you still need to look into each substage, like each small stages in those big stages. For instance, freeze one part and then unfreeze the other part, and then do the flip. How did you do that? Those parts? I mean, how did you do this? How did you fine tune? Let's say if you want to get the best first 5 stage, did you really tune it a lot in order to get the best model after the 5th stage?
Well, I will say if I have time to choose a better or much more better hyperparameter settings of hyperparameters, the performance will be at least 0.01 better than the performance I have now. But yeah, I did not do many of the ablation studies to choose the hyperparameters. So there is room to do that. Yeah.
I see.
Yep. Do we have any other questions? I think this is a really interesting discussion.
So assume there's any extra like 0.1%, if possible.
Yeah.
If you can try harder, I see.
And I mean, one final question maybe for me is like, so you said, I think VIT H Lion was released 15 days before the deadline, but you were able to repeat the 15 steps actually.
Yeah.
To train it, to fine tune it.
Yeah.
Mm-hmm. Yeah. 1 step per day.
Yeah, that's true. So I just use my server from a laboratory. So there are many just like students who also use this server. So I just want them did not crash my program that I'm currently training. Yeah.
Nice. Yeah.
So basically, yeah, from the initial clip checkpoint to the ones that was released pretty recent before the deadline, did you change any hyperparameters or use the same set parameters, just redo the whole process?
The same one.
Okay,
I don't exactly remember, but I think it's the same one. I did not remember I do anything of the changing. If you see my augmentation, you will see that I did not do much of the augmentation, just horizontal flip and something like that. I did not do the mix up and cut miss. Yeah.
Yeah, I think that's all the questions on my side.
Yeah, I think from my side too. So it looks like from the side potentially too. Is that right?
Yes.
Yep. Thanks again, Shihal, for your time. I know you already had given a presentation at the workshop and making you give another one here, but I think it was great to actually do a deep dive on the techniques. Like the workshop was very quick and had time for 1 or 2 quick questions only. Congratulations again. Excellent work. I mean, it's impressive that basically you by yourself, with your advice from your advisor, but almost single-handedly you implement all these things and win this challenge. So yeah, congratulations again.
Thank you.
Congrats.
Yeah, congrats.
Congratulations.
Thank you.